So hello everyone, welcome back to this week's algebraic graph theory seminar. This week, Jephian is going to tell us about the inverse eigenvalue problems of a graph.
Okay, so thank you, Tina, and thanks, Sabrina, for the invitation. I guess you guys can hear me well, right? Okay, I just want to make sure that I'll mute myself. Okay, so again, thanks the Waterloo team for the invitation, and thanks everyone for changing the time for me. I know it could be late or super late for some time zone. But anyway, I want to talk about the inverse eigenvalue problem of a graph. And that's one of the favorite topics that I have been doing for a while. So I will just jump into the definition and then just provide some motivation and some history to see why we care about this problem. Okay, so I will focus on a graph, a simple graph, undirected graph. And I will define the set of matrices. It is called S of G. And it's easier to look at that by an example. Say, for example, I have a path on 4 vertices. I can label that by 1, 2, 3, 4, and then associate that with the family of matrices. And the way that I associate the matrix is that if 1 and 2 has an edge, then the corresponding entry has to be non-zero. This star sign means it's a non-zero number, and I don't know what it is. And in contrast, if 1, 3, say, it is not adjacent, then it has to be 0. And so overall, in this example, we have 1, 2, 2, 3, and 3, 4. They are non-zero. And the last condition is that for diagonal entries, it's okay to be 0 or non-zero. And I want this matrix to be symmetric. So you can think of that this matrix is more like a weighted adjacency matrix with the free diagonal. And when I collect all these weighted adjacency matrices, then I say the set of these matrices as the S of G. Okay, so it's basically like if I know a matrix, then I can calculate its spectrum. So that's not a problem. We learned that in linear algebra. And now the opposite is like if I give you a graph, I say I want the matrix, it looks like this pattern. And I also tell you that, okay, today I want the spectrum to be 1, 2, 3, 4. Is it possible to find a matrix of this pattern such that the spectrum is exactly the designate values that I just given? Okay, so that's the essence of the inverse eigenvalue problem. Or you can say that, okay, when I ask the inverse eigenvalue problem of a particular graph G, then I'm basically thinking of all the possible spectrum that can occur in the set of matrices S of G. So there are a few reasons to study this. One thing is like if you think of this as a mass spring system, and then basically you can use the matrix to record the weight of each masses, and you can also record the coefficient or the stiffness of the spring on the off diagonal. So there are some numbers that we don't know what it is. And we also have something that control the spring. But just somehow that if I just look at this system, we might not know the detail of the number. So all we have is just a pattern. When we look at a graph, we know it looks like this. And in the vibration system, the eigenvalue will govern the whole vibration, right? So basically it is, if I give you the certain situation of the vibration, can it occurs in this mass spring system? That's kind of one way to look at that. And then the other way to think of that is just, this is just a fundamental problem, right? Suppose I look at the matrix and I only know the pattern looks like this, then what can I say about the spectrum? So that's the idea that why I want to study the inverse eigenvalue problem. So it turns out that just look at the spectrum, there are just way too many combination. We know the symmetric matrices, the eigenvalues must be real, and there are some multiplicities, but there are just way too many combinations. So I usually like to visualize the spectrum in the following way. So all eigenvalues are real, so I can arrange the eigenvalues from small to large. Say I have q distinct eigenvalues for a particular matrix. Then I can draw a bar graph and say, okay, lambda 1 has a certain multiplicity, lambda 2 has a certain multiplicity, and it is something like this. So there are a few things that we can ask about the feature of this spectrum. For example, if you look at all the matrices in S of G, what is the maximum height of this picture, right? Different picture has a different height. In other words, if I look at a matrix in S of G, then what is the maximum multiplicity of this spectrum? And if I run through all the matrices in S of G, what is the maximum of the maximum multiplicity of all the matrices? On the other hand, I can look at the width of that. I can think about, okay, if you give me a matrix, then I have the number of distinct eigenvalue, and I want it to be shorter as possible. So among all the matrices in S of G, what is the smallest q that I can find in S of G? There are other things. For example, you can be more refined, say ranging from 1 to q, the multiplicity m1, m2, m3. This is denoted by the ordered multiplicity list. So you can say, okay, for example, 1, 3, 1, dot, 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 2, is this kind of multiplicity possible inside S of G? So these are a few questions that we can ask. So what are the possible M of G? Or what are the possible maximum multiplicity over all the matrices and all the eigenvalues? Or what is the minimum number of distinct eigenvalues in S of G? So I will start with some basic examples and then run through some example to see how historically mathematicians are working on this problem and how it evolved. So if I just think of a path on n vertices, then its corresponding matrix will looks like this tridiagonal matrix, and it is irreducible. Okay, and in particular, all these off-diagonal entries must be non-zero, and while the diagonal entries, there could be anything. It is symmetric. So if I think of what are the possible spectrum that can occur as a matrix, the spectrum of a matrix here, then what can I do? Can say, for example, 3, 3, 2, 2, 2, can it be an eigenvalue? Can it be a spectrum of P5, something like that? So it turns out that it is quite restrictive. So for example, if I just take out the last row, then I will realize that, okay, starting from first row, second row, up to n-1 rows, these things looks like an action form. So this tells us that from the first row to the n-1 row, these rows must be independent. And as a consequence, we know that any matrix looks like this. The rank is at least n-1, and the nullity is at most 1. And somehow this statement does not change if I change the diagonal. So you give me a matrix A, then I shift the diagonal by lambda, then it becomes A minus A. A minus lambda I, then this matrix is still a matrix in S of Pn. So it follows the same philosophy that I have the nullity of this one is less than or equal to 1, which is actually the multiplicity of eigenvalue lambda. So in the end, just by some combinatorial observation property, then we know any matrix like this, then its eigenvalue multiplicity cannot be more than 2. It must be 1 or less. Okay, so that is to say the eigenvalues must be all simple. It must be looks like this. It turns out that back to 76 and Gray Wilson and Hall, both of them independently published papers saying that this is the only condition that you need to achieve this a matrix in S of Pn. So that is to say, as long as you have n distinct real numbers, then it could be realized by a matrix in this set. And in other words, whenever you take in other direction, whenever you take a matrix from here, then all the eigenvalues must be distinct. And interestingly, actually these two papers both published in LAA, which is one of our favorite journal, right? But back to 76, they independently published something quite similar. Now let's move on to cycle. Cycle is a little bit different, and that's one of the interesting things that I want to introduce. Okay, so for cycle, it is basically similar to a path, except that for cycle, I also have an edge from vertex 1 to vertex n. Okay, so if I look at this pattern, then I can do similar things, but the argument will be a little bit different. I need to remove the last row and also remove the first row. And once I do this, then the row number 2, 3, 4 up to n-1 following the same argument, they are always independent. So we got the conclusion saying the rank is at least n-2, and the nullity is at most 2. And again, the multiplicity is also at most 2. Now we might wonder, well, is this the only condition that you need to make it a spectrum in this set? Then it turns out that this is not the correct answer. The correct answer is actually something looks like this. It has a nice pattern, but it's a little bit absurd of what's going on of these conditions. So if you look at this one, for example, you will see that, okay, multiplicity 2 is possible, and then multiplicity 2, and this one is like a 1, 2, 2, 2 for the multiplicity list. But if you think of that once more, then you'll realize that not all the multiplicity lists are possible. For example, if you have a C5, you have 5 eigenvalues, and then the multiplicities are 2, 1, 2 correspondingly, then it does not belong to any of these two patterns. Right? If it is 2, then it must be this case because lambda 1 equal to lambda 2 is not the second case. Now, if you follow the first case, then it says that lambda 3 can possibly be the same as lambda 4, but lambda 4 is not the same as lambda 5. So it is impossible to be 2, 1, and 2 because 4 and 5 cannot be the same. So another way to think about this is that if you have 2 eigenvalues of lambda 2, say for example, lambda 1, lambda 2, okay, this is one eigenvalue of multiplicity 2. The other eigenvalue of multiplicity 2 must be 5 and 6. And the number of eigenvalues in between must be an even number. That's the other way to think about it. So beyond the condition that all the multiplicity must be at most 2, then there is an extra condition saying between any eigenvalues of multiplicity 2s, the number of eigenvalues in between must be even. And it turns out that back to 80s, that Ferguson proved that this is the two conditions that we need for S of Cn. All the eigenvalues of S of Cn looks like this. And in contrast, whenever you give me a set of real numbers that looks like either case 1 or case 2, then you can go back and find the matrix in S of Cn such that it has the prescribed spectrum. So now that's something a bit more interesting, right? Because just using the multiplicity is not quite enough to describe the situation of the spectrum. So then I will spend maybe the next 10 minutes to explain this phenomena. And it turns out that it uses some theory in symmetric matrices, and it also used something called eigenvalue, eigenvector identity, and it is a combination of several things. It's not hard, but it's a beautiful result, so I want to introduce this thing. Okay, so before moving this page, I want to emphasize that this is a path, right? So if you take out one column and one row, say the last column and last row, then it becomes a matrix of Pn. So in order to study this Cn, let's forget about that for a while, and then we will focus on Pn for a while. Okay, now there are at least 2 or 3 pure linear algebra results, not too much related to a graph that I want to share. So first, suppose I have a matrix that is a matrix of a path. Basically, it is a symmetric matrix, tridiagonal, and irreducible. And you know, it is a matrix we did not emphasize what is the value. We only know it is non-zero. So it could be positive or negative. And it turns out that whenever you have a matrix of this form, then you can associate with a diagonal 1 minus 1 matrix, and you can use that to do similarity. So I can find a D matrix, and then D inverse is itself, such that the whole thing becomes positive on the off diagonal. So for example, I just assign the first one as 1. And then I see, okay, this is already a positive number, so I can associate this as 1, so that after the multiplication, then the new matrix is positive. But now this is a -4. I want the new matrix to be positive on the off-diagonal entries. I want this -4 to be positive. So I can change this value to be -1. So because it is 1 and -1, this 4 will become positive later. And this -6 again says that your third entry, fourth entry has to be the opposite sign. So you can assign this one as the positive one. So overall, if you do this, this matrix has the same diagonal, but the off-diagonal entries will become the same quantity, but becomes positive. And such a technique is called as signature similar, and this diagonal matrix is called a signature matrix. So overall, any tridiagonal matrix is signature similar to a matrix whose off-diagonal entries are positive. That's the first thing. And secondly, it's quite interesting. Again, it was discovered by Ferguson, and it can also be implied by the other result by Fiedler. But anyhow, if I have a matrix, for convenience, we just say that it is all positive on the off-diagonal entries, okay? So if I have a matrix from S of Pn and the off-diagonal entries are all positive, then I can do the diagonalization with all the real eigenvalues, and the eigenvectors are orthogonal. And suppose that I arrange the eigenvalues from small to large, and then I also arrange the eigenvectors correspondingly, then it looks like this. Each column is corresponding to the eigenvector. And you see this is actually the Perron eigenvector, Perron vector, right? It's all positive. But there is an interesting thing happening here. This is the, if you look at the first vertex and the last vertex, it is positive, negative, positive, 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 negative, positive, positive. So it turns out that whatever the matrix you give me here, the corresponding matrix of eigenvectors from left to right, the product of the first entry and the last entries, it will change the sign alternatingly. It is the product is minus, the product is positive, the product is minus, and then the product is positive again. So in terms of the symbol, if you have several eigenvalues, if you multiply the first entry and the last entry, and then you change the eigenvectors I, then it is sign alternating. Until the biggest one, it is always of the same sign. Okay, so with this, then we are able to say a bit more about the cycle. Let me jump through the proof. Let me skip the proof for a while and then come back to see why this is true later. Okay, so now we can move back to the cycles. And remember, the cycle says that all the eigenvalues has multiplicity at most 2. And there is one extra condition saying if I have an eigenvalue of multiplicity 2 and the other eigenvalue of multiplicity 2, the difference between them must be even. This is Ferguson's result saying this must be true. And it's also the condition to realize the spectrum in S of Cn. So here is a reason, okay? I'm going to take a matrix from S of Cn. And as I mentioned before, if I remove the last row and last column, then this A removing the last row, last column, it is a matrix of Pn. And I want to say that for such a matrix and the two eigenvalues in between, the number of eigenvalues must be even. Okay, so now first step, I don't want to change the eigenvalue, so I do the similarity by the signature matrix. So I can assume that this part has all the non-negative off-diagonal entries. This is the first result that I used. And then notice that this B vector is spatial. This B vector is has the form that it has this 1n entry here, and it also has the n-1n entry. It is here. So it only has 2 non-zero entries, and x and y are non-zero. Okay, so now I want to study a little bit about the eigenvalues of A and also the eigenvalues of A taking out n. I assume the smaller matrix has eigenvalues from mu1 to mu n-1, and these are the corresponding orthogonal eigenbases. Now, according to the Cauchy interlacing theorem, if the bigger matrix has multiplicity 2, then the smaller matrix also have the same eigenvalue as well. Okay, so it is if this happens, then mu I also be the same eigenvalue. And you know this eigenvalue is multiplicity 1 because it is eigenvalue of a path matrix. It is a matrix of a path, so it is multiplicity 1. So it turns out that if you look at this matrix, and there is an eigenvalue that occurs here of multiplicity 1, and the bigger matrix has eigenvalue of multiplicity 2, then this means that multiplicity is increasing by 1 by bordering this B and C. In other words, to say that is that when you have a minus mu I and you want to increase this column, this new B matrix, this B vector must be in the column space of this matrix. And the same for this row. That is this one. Whenever I look at this matrix and I have a lambda I, mu I have the same eigenvalue, then when this happens, this smaller matrix, its column space must include the B vector. So this B vector is inside the column space. But I know that B vector is in the column space. In other words, B is orthogonal to the kernel of this matrix. And the kernel of this matrix is exactly the eigenvector, right? So this means that the kernel, this B vector must be orthogonal to the VI. And this happens only when VI has the nice first entry and the last entry, because B has a spatial form, X and Y. So when you multiply B and the VI, then the inner product is only doing the inner product of X and the VI1 and the Y and VIN. So the sign of V1 and the VN minus 1, this one is a spatial sign. But somehow the sign of XY is a fixed term. You know what the sign it is. It is determined when we associate this matrix A. So this cannot be any sign. It's either just fixed to be positive or fixed to be negative. So that is to say, this I can only happens in the certain position. You cannot happens in any position. And sign is sign alternating. So whenever you have two things, I and J both happens, then this means that I and J, the difference is even. Okay, so I just want to emphasize that I guess I will skip the proof of this result, saying why it is alternating. But I just want to say that back to 1980, Ferguson cited a result that is so-called the eigenvector eigenvalue identity. And if you follow some like scientific media or some news, then this identity was sort of rediscovered by Terry Tao in 2019. Some news says that he discovered this identity, and a few days later, somebody says that, okay, this was actually known much earlier. And I will just briefly go over the idea of this theorem instead of giving a proof. But it is saying that if you consider A minus lambda I, where lambda is multiplicity 1, okay, so this is a rank n minus 1 matrix. And when we consider its adjugate, then its adjugate will look like something like this. It is a huge coefficient and multiplied by a matrix. And this matrix is exactly the outer product of VI and VI, the kernel of this previous matrix. Okay, so for example, the adjugate multiplied by itself is equal to determinant times identity. And now the determinant is equal to 0. So this adjugate multiplied by itself must be 0. So that's reasonable that this adjugate its column is spanned by the kernel and its row is also spanned by the kernel. And so this eigenvector eigenvalue identity is basically describing the behavior of the adjugate when the matrix has rank n minus 1. And just somehow that back to Ferguson in 1980, he already cited a result by Cauchy saying that this eigenvector eigenvalue identity was known, and he used this to prove the result about the cycle. Okay, to conclude this section, I would say generally the inverse eigenvalue problem is try to study the spectrum behavior of a matrix whose pattern is known, but we don't know the values. And there are several techniques that can be involved. For example, we study the independence of the rows. I just look at the pattern, I know certain rows are independent. And this technique was later evolved as a technique called zero forcing. And there are some other combinatorial tools, say unique shortest path and some variants of zero forcing. Some combinatorial things can be involved. And On the other hand, there are a lot of interesting things about theory of symmetric matrices. For example, interlacing, eigenvector, eigenvalue, identity, Rayleigh quotient, and something. Oh, yeah, and this is perfect to introduce in this seminar, right? So in Gassol's book, also mentioned a result about the multiplicity of an eigenvalue in a tree. And this lemma, of course, it is not referred to Gassol's lemma in his book, but it was referred to Gassol's lemma in Hammer's book, The Spectra of Graphs. So anyhow, there's another, just a beautiful theorem about the eigenvalues of a tree that can help us to understand the eigenvalue or multiplicity of a tree. And quite recently, some idea about inverse function theory, implicit function theory, some analytic tools also allow us to perturb the matrix a little bit. So I just want to say this is a kind of a beautiful field, and whoever is interested in this problem, then you can always find a role to play with. And if you are curious about this problem and want to have a better idea of that, there is about 5-page article that was published in Notice of AMS. So you can have a look of that. So that's the first part of my talk. I will pause for a few seconds and to see if there is any questions. Okay, so if not, then I will use the next 10 minutes to introduce a little bit different aspect of this inverse eigenvalue problem. So pretty much what I did before is telling you for path and for cycles, the shape of the spectrum is restrictive. You cannot have arbitrary shape of the spectrum. The multiplicity is bounded, and then you cannot have two eigenvalues of multiplicity 2 with some condition, right? And somehow I did not tell you how to construct this matrix. If I go back to these results, say for example, I just told you that, well, somebody told that whenever you give me this metric, give me these real values, then I can find the matrix. But how? Now I want to pay some efforts to tell you, whenever you give me some number, how can I find the matrix? Okay, so I guess I can skip this one. The overall idea is now give me a matrix, give me a graph, and give me some real eigenvalues. And I'm trying to construct a matrix that looks like this, and with a given spectrum. So these techniques are developed quite recently, and basically the idea is to perturb the matrix in a nice way. Let's look at the picture first. Say I have a matrix, and this matrix obviously has the spectrum 1, 2, 3, 4. Okay, so now suppose I want the matrix whose pattern is given by the path. So it should be tridiagonal, and its spectrum is exactly 1, 2, 3, 4. Then what can I do? So naively is I start with this diagonal matrix, but the pattern is not correct. So one thing we can do is try to perturb the matrix into a nearby matrix such that it still have the same spectrum, but now I have a little bit more non-zero entries here. And if this is successful, then I come up with the matrix of the path such that the spectrum is also 1, 2, 3, 4. So in terms of the graph, you can see this is the matrix of 4 isolated vertices, and this is the matrix of P4. So here is the statement of the lemma. Let's say G and H prime be two graphs. You can imagine G is the 4 isolated vertices and H prime is P4. Now they have the same set of vertices and H prime has a little bit more edges. And so suppose from the smaller graph, I have a matrix A and it has some condition called SSP to be defined later. Okay, then there will be, this lemma tells you that there will be a matrix A prime that is in the new graph such that the spectrum is the same. And it also has the nice property SSP. And then A prime is the perturbation of A. It can be chosen arbitrarily close to A. Okay, so the thing is, what is this SSP? And then if this is true, then you can create a lot of matrices with a nice spectrum. Without really doing that, you can construct the matrix implicitly. Okay, so I will just give the big picture of that and see how it goes instead of giving the detail of the proof. I will use a concrete example in R2 because I myself, I cannot visualize the space of matrices. Even the 2x2 symmetric matrices, it has 3 dimensions, right? And higher order matrices has a much higher dimension. So let's say I have a vector A, and then this vector A is just in 2 dimensions, so it has 2 numbers. Okay, you can imagine that the origin is here. But I'm going to do 2 types of perturbation on this vector A. The first one, I'm going to add this vector A with some direction, left and right. Okay, if I add the B times E1, E1 is 1, 0. Okay, if I add some scatter of E1 to A, then A will be running on this line. So if I do this kind of perturbation, then the value of Y is the same. It does not change the Y value. Okay, and on the other hand, I can do the rotation. This is the rotation matrix. If I do the rotation of A and imagine that the origin is here, then the A will run in on this circle, right? And the norm does not change. So it's like I have a 2 perturbation and one is preserving the Y value. The other perturbation is preserving the norm. And both of them are nice. And I want to see if they can cooperate nicely. Okay, so I am going to do this perturbation sequentially. I want to do the rotation first and then do the left-right perturbation. And now if I apply this perturbation, I have 2 numbers, 2 inputs. I can do left, right, I can rotate. And then the output is also a two vectors. Okay, so this is a R2 to R2 function. So I can calculate its Jacobian matrix. If I calculate its Jacobian matrix and it is invertible, then I know according to the inverse function theory, then there is a neighborhood such that all the points nearby, you can reach it by some theta and then some beta prime. In other words, just whatever the W you give me, as long as it is very close to A, it can be reached by this 2-step perturbation. You can go by orange and then go by blue. And yet the nice thing is that if you look at this intermediate points, you perturb it by the rotation and then perturb it by the horizontal perturbation. And before that, you just reach intermediate points. This point has the same Y value as W. It has the same norm as A. So that is to say, for any Y value nearby, you can always find a vector A prime with the same norm. Well, for the 2x2 matrix, for the 2-vector, this is obvious, and for sure, I'm just doing something using heavy machinery, right? But there are a few things that I want to say. First, if you do the derivative with respect to theta, then it is doing the derivative along this trajectory, and the output is a tangent vector on this direction. And it is this tangent vector is also one of the column in this Jacobian. And same for B. If you do the B, then you are calculating the derivative along this trajectory. And then the tangent vector is another column in this vector, in this Jacobian. So this Jacobian is invertible if and only if the two vectors are independent or it span the whole area, whole space. And that is to say, if you look at the tangent and tangent, if these two tangents is span the whole R2, then this statement holds. And without saying too much, in the end, I want to say the story like this. Let me see, if I can find that. Okay, so now I want to run the same story starting with the matrix A. It is the matrix that I have, but it's a correct pattern, but it does not have the it is the correct spectrum, but not the correct pattern. So what I'm doing is that I want to move the blue entries a little bit so that it preserves the same pattern. Okay, and on the other hand, I want to kind of rotate that the matrix by similarity. So I can do the similarity perturbation of matrix A without changing its spectrum. And if I apply some inverse function theory with some accurate computation, then I can say any nearby matrix that I can reach by this two-step perturbation. So that is to say, I just pick one matrix that is nearby by adding some epsilon. Okay, this matrix is terrible. Its pattern is correct, but the spectrum is not correct, right? But somehow, according to the inverse function theorem, this matrix can be reached by two-step. I can go by orange and then go by blue. And if I stop at the intermediate one, then this one has the same pattern as M. And that's nice because M has the right pattern. And it has the same pattern as A. And that's also nice because A has the correct spectrum. So now I found a matrix A prime, which is in between, such that the pattern and the spectrum are both correct. So that's basically the idea of the supergraph lemma and how to construct a matrix in this way. And so that's a power of using the inverse function theory. And in the end, I just want to say that the same function, you can consider, you can swap the order of the perturbation. You can do the orange first and then do the blue second. You can do the blue first and then do the orange secondly. And it turns out that just switching these two things will give you a different lemma called the bifurcation lemma. But I think I will just stop here using this picture. And in the end, if you are curious about more IEPG things, then there is a book here. And I just want to do some advertisement that if you are into the ILS conference, then the ILS conference 2025 is going to be in Taiwan. And thank you very much.
Thank you.
Thank you.
Very nice talk. So any question for Jephian? Yes. Hajime Tanaka, you can.
Yes. So thank you very much for the nice talk. So I have one question. So maybe I have missed something. So but today you talked about paths and cycles as examples.
Yes.
And So are there more examples other than paths and cycles?
I see. Yeah, thank you for the question. Yes. Well, yes and no. So, for example, the complete graph, it's fairly easy. For complete graph, the solution is like, okay, you can reach basically every spectrum because you have all the non-zero entries. Okay, so it is doable. But the only spectrum that you cannot do for a complete graph is the spectrum of all the same eigenvalues. Say K5, you cannot reach the spectrum 1, 1, 1, 1, 1. It's because that this such spectrum is only realized by the identity, the scalar of identity matrix. So for basically for complete graph, it is doable, but quite unfortunate is that even for tree, it is still open. Some family of trees, it's known, say generalize a star or a star, and it is doable. But in general, even for tree, we don't know how to solve the inverse eigenvalue problem of that. And I hope this answered the question a little bit.
I see, thank you. There is a comment from Steve Butler. I see.
Oh.
Okay, 5 vertices and 6 vertices. Oh, I see. So, but then what about, maybe you can think about graph operations. Yeah, maybe direct products of paths. I'm not sure. But anyway, I have one other comment. So today, in the discussion of cycles, you talked about some lemma about sign changes. But I believe this also follows from a general result about Sturm sequences of orthogonal polynomials. Sturm sequences.
Yes.
Yeah, so you can find it in the book by Chris Corsier, Algebraic Combinatorics. This one.
Yeah. Okay.
Yeah. This is just a comment.
Yeah. Thank you very much. Yeah.
Anyway, thanks a lot.
Okay, thank you. Yeah. I think that's you're right, and right. I wasn't aware of that, and I will check it out from the book. Thank you.
So, any other question for Jephian? If there's none, let's thank Jephian again. Thank you.
Yeah. Okay. Thank you, and thank you for everyone.